Tonight, we're going to explore something that has sent shockwaves through the entire scientific community. In December 2021, humanity launched the most powerful telescope ever built into space, and within months, it started sending back images that made astronomers question everything they thought they knew. Galaxies that shouldn't exist, stars that formed too early, black holes that grew too fast. One by one, the James Webb Space Telescope has been challenging our most fundamental assumptions about the cosmos. But here's what makes this truly fascinating. Webb isn't breaking physics. It's revealing that the universe is far stranger, far more complex, and far more mysterious than we ever imagined. And by the end of tonight, you're going to understand exactly why scientists are scrambling to rewrite the textbooks. Before we dive in, if you find these kinds of deep explorations of the cosmos interesting, a quick like or subscribe would really help the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let us start with the telescope itself, because understanding what the James Webb Space Telescope actually is helps explain why its discoveries are so profound. This is not just a bigger version of Hubble, this is a fundamentally different kind of observatory, built to see things that no telescope has ever seen before. The engineering that went into this machine represents humanity's most ambitious attempt to peer back through cosmic time to witness the universe's earliest chapters. The James Webb Space Telescope launched on December 25th, 2021, atop an Ariane 5 rocket from French Guiana. After decades of delays, budget overruns, and engineering challenges that nearly killed the project multiple times, humanity's most ambitious space telescope finally left Earth. The original budget was roughly $1 billion. The final cost exceeded $10 billion. The original launch date was 2007. The actual launch came 14 years later. But when you understand what this telescope had to accomplish, the delays and expenses begin to make sense. Unlike Hubble, which orbits Earth at an altitude of about 540 kilometers, Webb travels much farther from home. Its destination was a point in space called the second Lagrange point, or L2, approximately 1.5 million kilometers from Earth. At this location, the gravitational pulls of Earth and the Sun balance out in a way that allows Webb to orbit the Sun while staying in a fixed position relative to our planet. This arrangement is crucial because Webb needs to stay cold, incredibly cold, colder than almost anywhere on Earth has ever been. You see, Webb does not primarily observe visible light like Hubble does. Webb observes infrared light, which is essentially heat radiation. Everything warm emits infrared light, including the telescope itself and its instruments. If Webb's detectors were at room temperature, they would blind themselves with their own thermal emissions. The faint infrared whispers from galaxies 13 billion light years away would be drowned out by the telescope's own heat signature. So Webb carries a sunshield the size of a tennis court, made of 5 layers of a material called Kapton. Each layer is thinner than a human hair. This sunshield blocks the light and heat from the Sun, Earth, and Moon, creating a permanent shadow where the telescope's instruments can cool to temperatures as low as -233 degrees Celsius. That is roughly 40 degrees above absolute zero, the coldest possible temperature in the universe. At these temperatures, the telescope's own thermal emissions fade to negligible levels, allowing it to detect the faintest infrared signals from the most distant objects in existence. The mirror itself represents a marvel of precision engineering. Webb's primary mirror spans 6.5 meters across, made of 18 hexagonal segments, coated with a microscopically thin layer of gold. Gold is used because it reflects infrared light with exceptional efficiency. Each hexagonal segment had to be polished to tolerances measured in nanometers, a level of precision that would make a mirror segment feel smoother than anything you have ever touched. If you scaled one of these segments up to the size of the continental United States, the largest surface imperfection would be about 4 inches tall. The mirror is so large that it could not fit inside any existing rocket while fully assembled. No rocket fairing was wide enough to accommodate a 6.5 meter mirror in its operational configuration. So engineers designed the mirror to fold up for launch like elaborate origami, then unfold in space through a carefully choreographed sequence of mechanical operations. This unfolding process was perhaps the most nerve-wracking part of the entire mission. Webb had 344 single points of failure, mechanisms that had to work perfectly, or the entire telescope would become an extraordinarily expensive piece of space debris. Unlike Hubble, there was no possibility of sending astronauts to fix problems. Hubble orbits close enough that space shuttle crews could visit for repairs. Webb operates at a distance roughly 4 times farther than the Moon. No crewed spacecraft can reach it. Every component had to work the first time. Engineers spent years testing every mechanism, running simulations, preparing contingency plans for every conceivable failure mode. They deployed the sun shield on Earth dozens of times. They practiced the mirror unfolding sequence repeatedly. They analyzed every actuator, every motor, every cable, every latch. But when the telescope actually began its deployment sequence in the cold vacuum of space, 1.5 million kilometers from any possibility of repair, everyone held their breath. The deployment took about 2 weeks. First, the sun shield unfurled, a process involving hundreds of release mechanisms, pulleys, cables, and tensioning motors, all working in precise sequence. Any single failure could have left the sun shield improperly deployed, unable to protect the instruments from solar heating. Then the secondary mirror swung into position at the end of 3 long booms, placing it precisely at the focal point of the primary mirror. Finally, the 2 side wings of the primary mirror folded into place, and the 18 hexagonal segments began their alignment process. This alignment was itself a remarkable achievement. Each mirror segment has actuators capable of adjusting its position and angle with nanometer precision. Over a period of months, engineers sent commands to these actuators, nudging each segment until all 18 mirrors worked together as a single, perfect optical surface. The light from a distant star had to hit all 18 segments and focus to a single sharp point. The precision required was equivalent to aiming 18 flashlights from New York and hitting the same penny in Los Angeles. When it was all done, when every mechanism had worked flawlessly against odds that kept engineers awake at night for years, scientists around the world breathed a collective sigh of relief. Webb was operational. The most complex space observatory ever built has survived its deployment. And then it started sending back images that challenged everything astronomers thought they understood about the early universe. The first full-color image released to the public came on July 11th, 2022. It showed a galaxy cluster called SMACS 0723, a massive collection of galaxies whose combined gravity acts as a cosmic magnifying glass. bending and amplifying light from even more distant galaxies behind it. This effect, called gravitational lensing, was predicted by Einstein over a century ago. Massive objects warp space-time, and light follows the curvature of space-time, causing distant objects to appear magnified and distorted when viewed through the gravitational lens of a foreground cluster. That single image, covering a patch of sky about the size of a grain of sand held at arm's length, revealed thousands of galaxies stretching back billions of years. Some appeared as smeared arcs, their light bent and stretched by the gravitational lens. Others appeared as tiny red dots, their light so ancient and so redshifted that they glowed only in the infrared wavelengths where Webb's instruments operate. But it was not just the beauty of the image that stunned astronomers. It was what they found hiding in the data. Among those distant points of light were galaxies that appeared far too mature, far too massive, and far too well-formed for how early they existed in cosmic history. Galaxies that should not exist according to our best models of how the universe evolved. Galaxies that seem to have formed impossibly fast in the cosmic dawn. To understand why these early galaxies are so surprising, we need to talk about what the cosmic dawn actually means. This is one of the most important chapters in the universe's history, and it is precisely the era that Webb was designed to study. Understanding this era requires traveling back to the very beginning of everything. The universe began with the Big Bang approximately 13.8 billion years ago. In the first few 100,000 years, the cosmos was filled with a hot, dense plasma of particles. Protons, electrons, and photons collided constantly in a seething ocean of energy. Light could not travel far because it kept scattering off the charged particles. Every photon would travel only a short distance before hitting an electron and bouncing in a random direction. The universe was essentially opaque, like being inside an incredibly thick fog that extended in every direction forever. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This moment, called recombination, changed everything. With electrons now bound to atoms rather than roaming freely, photons could finally travel without constant scattering. Suddenly, light could move freely through the universe. The cosmic fog lifted. The light released at this moment is what we now observe as the cosmic microwave background radiation. This is the oldest light in the universe, a faint glow that permeates all of space, stretched by 13.8 billion years of cosmic expansion from its original visible wavelengths into the microwave range. When you look at static on an old television set, a tiny fraction of that noise comes from cosmic microwave background photons that have been traveling since the universe became transparent. But after recombination came a period astronomers call the Cosmic Dark Ages. There were no stars yet, no galaxies, no sources of light except the fading glow of the cosmic microwave background. The universe was filled with neutral hydrogen gas, cooling and spreading through expanding space. For roughly 100 to 200 million years, the cosmos existed in darkness. If you could somehow transport yourself to this era, you would see nothing. Complete blackness in every direction, no stars to navigate by, no distant galaxies to contemplate, just an infinite void of invisible hydrogen gas. Then, something remarkable happened. The first stars began to form. These first stars, called Population 3 stars by astronomers, were unlike any stars that exist today. They formed from pristine hydrogen and helium gas that had never been processed through stellar interiors. They contained no heavy elements because heavy elements like carbon, oxygen, and iron are only created inside stars through nuclear fusion. The first generation of stars had to form without these elements, and this changed everything about how they formed. In today's universe, heavy elements help gas clouds collapse into stars. When a gas cloud contracts under its own gravity, it heats up. This heat creates pressure that pushes back against gravity, potentially stopping the collapse. But heavy elements can radiate away this heat efficiently, allowing the cloud to keep collapsing. Without heavy elements, the primordial gas clouds of the early universe could not cool efficiently. Only the most massive clouds could overcome this limitation and collapse under their own weight. As a result, the first stars were giants. Models suggest they were perhaps 100 to 300 times the mass of our Sun, possibly even larger. For comparison, most stars today are smaller than the Sun. These primordial behemoths burned incredibly hot and bright, their surfaces reaching temperatures far exceeding any star in the modern universe. They emitted fierce ultraviolet radiation that began ionizing the neutral hydrogen around them, creating expanding bubbles of hot plasma in the dark cosmic sea. But massive stars live fast and die young. A star like our Sun will burn for roughly 10 billion years. A star with 100 solar masses might last only a few million years before exhausting its fuel. When these first stars died, they died violently. Many exploded as supernovae of unprecedented power. Others may have collapsed directly into black holes. These explosions scattered the first heavy elements into space, seeding the universe with carbon, oxygen, silicon, iron, and all the other elements that would eventually form planets and living things. The ultraviolet radiation from these first stars, along with the light from their explosive deaths and the radiation from gas falling into the first black holes, began to transform the universe. This radiation ionized the neutral hydrogen gas, stripping electrons from atoms and creating bubbles of ionized plasma that grew and merged over hundreds of millions of years. Eventually, these bubbles filled the entire universe, completing a process called reionization by about 1 billion years after the Big Bang. This period, from the formation of the first stars through reionization, is the cosmic dawn. It is when the universe transitioned from darkness to light, from simplicity to complexity, from a uniform sea of hydrogen to the elaborate structures of stars and galaxies we see today. And it has been one of the most challenging eras to study because it happened so long ago that the light from this period has been traveling for over 13 billion years. Here is where Webb's infrared vision becomes crucial. When light travels through expanding space, its wavelength gets stretched along with the space itself. Blue light becomes red light. Red light becomes infrared. This is called redshift, and the farther light has traveled, the more it has been redshifted. Light from the cosmic dawn has been stretched so much that what was originally ultraviolet or visible light has now become infrared, invisible to human eyes and to telescopes designed for visible wavelengths. Hubble could see some of this light, but only barely. Hubble's instruments were not sensitive enough to detect the most distant, most redshifted objects with clarity. Webb, designed specifically to observe infrared light with unprecedented sensitivity, can see far deeper into cosmic history. It can observe galaxies that formed just a few 100 million years after the Big Bang. galaxies that have been invisible to every previous telescope humanity has ever built. And this is where the surprises began. When astronomers pointed Webb toward the distant universe, they expected to see small, irregular, chaotic proto-galaxies. According to our models of galaxy formation, the earliest galaxies should be tiny. They should be messy assemblages of young stars still in the process of organizing. The first galaxies should look primitive because they had not had time to evolve into the grand spirals and majestic ellipticals we see in the nearby universe. But that is not what Webb found. Instead, Webb discovered galaxies that appeared surprisingly mature. Some of them had disk shapes reminiscent of spiral galaxies. Some had stellar populations that looked old, suggesting they had been forming stars for hundreds of millions of years already. Some were far more massive than anyone thought possible at such early cosmic times. One of the most dramatic examples came from studies published in early 2023. Researchers using Webb's data identified several galaxy candidates at redshifts above 10. In astronomical terms, this means we were seeing them as they existed less than 500 million years after the Big Bang. Some of these galaxies appeared to have stellar masses of tens of billions of solar masses, comparable to the Milky Way today. This was shocking. According to standard models of cosmology, there simply had not been enough time for such massive galaxies to form. Stars need time to form from collapsing gas clouds. The process is not instant. Gas must cool, condense, fragment, and collapse under gravity. This takes millions of years even under optimal conditions. Galaxies need even more time to assemble from smaller building blocks through mergers and gradual accretion of matter. 500 million years should not be enough time to build something as massive as the Milky Way. Let me put this in perspective that makes the scale viscerally clear. The universe is 13.8 billion years old. 500 million years is less than 4% of that total age. Imagine a human lifetime of 100 years. 500 million years after the Big Bang would be equivalent to the first 4 years of that life. And Webb was finding fully formed, mature-looking galaxies at this cosmic toddler stage. It would be like finding a 4-year-old child with the physical development of an adult. The timeline simply does not work according to our models. Scientists began calling these objects impossibly early galaxies, though the word impossible is somewhat misleading. What it really means is that our models did not predict this. Our understanding of how fast galaxies can form and grow was incomplete. Something about the early universe worked differently than we assumed. Now, it is important to be careful here. Some of the earliest announcements about these surprisingly massive galaxies may have been premature. Determining the mass and age of a distant galaxy is incredibly difficult. You are working with tiny amounts of light that have traveled for billions of years. The photons collected by Webb from these distant objects may have started their journey before the Earth existed. The analysis involves complex models and assumptions that can sometimes be wrong. Initial mass estimates relied on photometric redshifts, essentially measuring the colors of galaxies and inferring their distances and properties from those colors. This technique is powerful but imperfect. It can be fooled by unusual stellar populations, by dust that reddens light, by active galactic nuclei that add extra brightness. In some cases, follow-up observations have revised the initial estimates. Some galaxies that initially appeared extremely massive turned out to be smaller than first thought when spectroscopic observations measured their redshifts more precisely. Some turned out to be at different distances than the photometric estimates suggested. Active galactic nuclei, powered by gas spiraling into supermassive black holes, can make galaxies appear brighter and therefore more massive than they actually are in terms of stellar content. But even after accounting for these complications, the basic finding stands. There are more bright, massive galaxies in the early universe than our models predicted. Galaxy formation was more efficient in the first few 100 million years than we thought possible. Something about our understanding of early cosmic evolution needs to be revised. What could explain this? Several possibilities have been proposed, and they are not mutually exclusive. The truth probably involves some combination of factors that our previous models underestimated. One possibility is that the first generations of stars formed more efficiently than we assumed. If gas could collapse into stars more readily in the early universe, perhaps because initial conditions were more favorable, or because some physical process we do not fully understand enhanced star formation, then galaxies could build up stellar mass faster than our models predicted. Another possibility involves the role of supermassive black holes. Many of these early galaxies might harbor rapidly growing black holes at their centers. The light from gas falling into these black holes could significantly boost the observed brightness of the galaxies, making them appear more massive in stars than they actually are. This would not solve the mystery entirely, since we would then need to explain how such massive black holes formed so quickly, but it could account for some of the discrepancy. A third possibility is that our cosmological models themselves might need adjustment. The standard model of cosmology, called lambda CDM, describes a universe dominated by dark energy and cold dark matter. This model has been incredibly successful at explaining observations on large scales. It accurately predicts the cosmic microwave background, the distribution of galaxies, and the expansion history of the universe. But perhaps at the smallest scales, in the earliest times, there are nuances we have missed. Some physicists have even speculated about more exotic possibilities. Could there be a form of dark matter that clumped more efficiently in the early universe than standard cold dark matter? Could the laws of gravity behave differently at early times or under certain extreme conditions? Could there be new particles or forces that affected how the first structures formed? These ideas remain highly speculative, but they illustrate how profound the implications of Webb's discoveries could be. When observations challenge fundamental models, everything is potentially on the table. What is remarkable about all this is how quickly the scientific community has mobilized to understand these findings. Within months of Webb's first data releases, hundreds of papers were published analyzing the early galaxy populations, proposing new models, testing alternative explanations. This is science at its best. New observations challenging existing theories and spurring rapid progress in understanding. And the early galaxies are just the beginning. Webb has also peered into the cosmic dawn in other ways. It has observed some of the earliest known quasars, extremely luminous objects powered by supermassive black holes that somehow grew to billions of solar masses within the first billion years of cosmic history. The existence of these massive black holes poses its own challenges to our models, since we struggle to explain how black holes could grow so large so quickly. Webb has detected signatures of the first heavy elements in distant galaxies, showing how quickly the universe became chemically enriched by the deaths of early stars. It has begun to study the process of reionization itself, mapping how the first light sources carved out bubbles of ionized gas in the neutral hydrogen fog. Each observation adds pieces to a puzzle that remains far from complete. The James Webb Space Telescope is essentially a time machine. Because light takes time to travel, looking at distant objects means looking back in time. When Webb observes a galaxy 12 billion light years away, it sees that galaxy as it was 12 billion years ago. The light arriving at Webb's golden mirror tonight left its source before Earth existed, before the sun ignited, before the atoms that make up your body had assembled into anything recognizable. But Webb's contribution to astronomy goes beyond just seeing farther back in time. It also sees with unprecedented clarity and in wavelengths that reveal things other telescopes miss. Infrared light penetrates dust clouds that block visible light. It reveals cool objects that do not emit much visible light. It shows us the universe in a way we have never seen before. And what the universe is showing us is that it is stranger than we thought. The early mature galaxies are perhaps the most dramatic example, but they are part of a broader pattern. Across multiple areas of astronomy, Webb is returning data that challenges our models, raises new questions, and forces scientists to reconsider assumptions they have held for decades. This is not a crisis for physics. It is an opportunity. Every time observations contradict theories, we learn something new. The history of astronomy is filled with moments like this, when unexpected discoveries led to profound advances in understanding. When astronomers first realized that galaxies were moving away from us in all directions, it led to the discovery that the universe is expanding. When they noticed that galaxies rotated too fast to hold together with their visible matter alone, it led to the hypothesis of dark matter. When they found that the universe's expansion is accelerating rather than slowing down, it led to the concept of dark energy. Now Webb is giving us a new set of puzzles. Galaxies that form too fast, stars that appear older than expected, structures that emerge too quickly from the primordial cosmic soup. These are not contradictions that overthrow physics. They are clues that point toward a deeper understanding. The laws of physics are not broken. They are richer and more complex than we realized. And that is perhaps the most exciting thing about Webb's mission. It is not just showing us what we expected to see. It is showing us what we did not expect. And that unexpected data is how science makes its greatest advances. The cosmic dawn, that transition from darkness to light that happened over 13 billion years ago, is now becoming visible to human eyes for the first time through Webb's infrared vision. What we are seeing challenges our assumptions, pushes our models to their limits, and reveals a universe that formed faster, evolved quicker, and achieved complexity sooner than anyone predicted. If the surprisingly mature early galaxies were Webb's only contribution to challenging our understanding of the universe, that alone would represent one of the most significant astronomical discoveries of our generation. But the telescope is also weighing in on one of the most contentious debates in modern cosmology. A puzzle that has been vexing scientists for nearly a decade and shows no signs of resolution. It is called the Hubble tension, and it might be telling us something profound about the fundamental nature of the cosmos itself. To understand the Hubble tension, we need to start with a basic fact about the universe that transformed our understanding of reality when it was first discovered. The universe is expanding. Every galaxy is moving away from every other galaxy, not because the galaxies themselves are flying through space like shrapnel from an explosion, but because the space between them is stretching. The fabric of the cosmos itself is growing larger over time. Space is not a static stage on which cosmic events unfold. Space is a dynamic participant in cosmic evolution, constantly changing, constantly growing. This expansion was first discovered by Edwin Hubble in 1929. Working at the Mount Wilson Observatory in California, with what was then the world's largest telescope, Hubble noticed that distant galaxies have light that is shifted toward the red end of the spectrum. More importantly, he noticed that more distant galaxies are redshifted more than closer ones. This relationship was systematic and unmistakable. This redshift happens because as light travels through expanding space, its wavelength gets stretched along with the space itself. Think of drawing a wave on a rubber band and then stretching the rubber band. The wave gets longer. The same thing happens to light traveling through an expanding universe. The farther light travels, the more it gets stretched, and the redder it appears to our instruments. Hubble realized that this relationship between distance and redshift meant the universe was expanding. Galaxies are not flying away from us through space. Rather, the space between all galaxies is growing, carrying galaxies along with it. This was one of the most profound discoveries in the history of science. The universe had a history. It was not eternal and unchanging. It was evolving. The rate of this expansion became known as the Hubble constant, usually written as h0. It tells us how fast the universe is expanding right now, typically measured in kilometers per second per megaparsec. A megaparsec is approximately 3.26 million light-years, a convenient unit for measuring cosmic distances. The Hubble constant has a simple interpretation. For every megaparsec of distance between two galaxies, those galaxies are receding from each other at a certain number of kilometers per second due to cosmic expansion. If the Hubble constant is 70, then galaxies 1 megaparsec apart are separating at 70 kilometers per second. Galaxies 2 megaparsecs apart are separating at 140 kilometers per second. The relationship is linear, at least for distances where relativistic effects remain small. Measuring the Hubble constant seems straightforward in principle. You measure the distance to a galaxy. You measure how fast it is moving away from us based on its redshift. You calculate the ratio. Do this for many galaxies at various distances. Account for their peculiar motions through space, and you can determine the cosmic expansion rate. But in practice, measuring cosmic distances is incredibly difficult. We have already discussed how challenging it is to determine distances to objects billions of light years away. Even for relatively nearby objects, only tens of millions of light years distant, accurate distance measurements require careful calibration of what astronomers call the cosmic distance ladder. The distance ladder works by using objects whose intrinsic brightness is known or can be determined through some independent method. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it must be using the inverse square law. Light spreads out as it travels, so an object twice as far away appears 4 times dimmer. These objects of known brightness are called standard candles, and they are crucial for measuring cosmic distances. The first rungs of the distance ladder use relatively nearby stars, whose distances can be measured through geometric methods. Parallax, the apparent shift in a star's position as Earth orbits the Sun, provides direct distance measurements to stars within a few thousand light years. These nearby stars calibrate the next rung. Cepheid variable stars are one of the most important standard candles for reaching beyond our immediate cosmic neighborhood. These are pulsating stars whose brightness varies in a regular, repeating pattern. What makes them so valuable is that the period of this pulsation is directly related to the star's intrinsic luminosity. A Cepheid that takes 30 days to complete one brightness cycle is intrinsically more luminous than one that takes 10 days. Measure the period, and you know how bright the star actually is. Compare that intrinsic brightness to how bright it appears, and you get the distance. This period luminosity relationship was discovered by Henrietta Swan Leavitt in 1912, and it revolutionized astronomy. Suddenly, distances to objects far beyond the reach of parallax measurements could be determined. Cepheids can be seen in galaxies up to about 100 million light-years away. Beyond that distance, even these luminous stars become too faint to measure reliably with current instruments. So astronomers use another type of standard candle for more distant measurements. Type 1. Supernovae are thermonuclear explosions of white dwarf stars. When a white dwarf accumulates enough matter from a companion star to exceed a critical mass called the Chandrasekhar limit, approximately 1.4 times the mass of the Sun, the pressure in its core becomes sufficient to ignite runaway carbon fusion. The star explodes in a catastrophic thermonuclear detonation. These explosions are incredibly luminous, briefly outshining entire galaxies containing hundreds of billions of stars. A single Type 1 supernova can radiate as much energy in a few weeks as the Sun will emit over its entire 10 billion year lifetime. And because of these explosions all occur at roughly the same mass limit. They all have roughly the same peak brightness after corrections for how quickly they fade. This uniformity makes them excellent standard candles that can be seen billions of light years away, across cosmological distances. By calibrating the brightness of Type 1 supernovae using Cepheid distances in nearby galaxies that happen to host such supernovae, astronomers can extend the distance ladder out to cosmological scales. This allows them to measure the Hubble constant using objects scattered throughout the observable universe. Using this method, a team led by Nobel laureate Adam Rees has measured the Hubble constant to be approximately 73 kilometers per second per megaparsec, with an uncertainty of only about 1%. This measurement has been refined over many years using observations from the Hubble Space Telescope, ground-based observatories, and now the James Webb Space Telescope. The precision is remarkable. The team knows the expansion rate to better than 1 kilometer per second per megaparsec. But here is where the tension emerges, creating one of the most significant puzzles in modern cosmology. There is another way to estimate the Hubble constant that does not use the distance ladder at all. Instead, it uses observations of the cosmic microwave background, that ancient light released when the universe was only about 380,000 years old, which we discussed in the context of the cosmic dawn. The cosmic microwave background contains tiny temperature fluctuations, variations of only about 1 part in 100,000, that reflect the density variations in the early universe. Some regions were slightly denser than average, others were slightly less dense. These fluctuations were the seeds that eventually grew into galaxies and galaxy clusters through billions of years of gravitational collapse. The denser regions attracted more matter, became denser still, and eventually formed the cosmic structures we observe today. By analysing the pattern of these fluctuations in exquisite mathematical detail, scientists can determine the fundamental parameters of the universe. The size of the fluctuations, their spacing, their statistical properties all encode information about the geometry of the universe, its composition in terms of matter and energy, and its expansion rate. This analysis requires sophisticated models of how sound waves propagated through the early universe, how photons and matter interacted, and how the universe has expanded over cosmic time. The most precise cosmic microwave background measurements come from the Planck satellite, a European Space Agency mission that operated from 2009 to 2013. Planck mapped the cosmic microwave background with unprecedented accuracy across the entire sky, revealing the primordial fluctuations with stunning clarity. The data from Planck remains the gold standard for early universe cosmology. When cosmologists use the Planck data to determine the Hubble constant, they get a value of approximately 67.4 kilometers per second per megaparsec. That is significantly lower than the value from the distance ladder method. The difference is about 6 kilometers per second per megaparsec, roughly 8%. At first, this discrepancy was thought to be due to measurement errors somewhere in the analysis. Perhaps the Cepheid calibrations were wrong. Perhaps there were systematic effects in the supernova measurements. Perhaps the Planck analysis had some unrecognized bias, or the models used to interpret the data were missing something. Scientists spent years checking and rechecking their methods, looking for errors that could explain the difference. But the discrepancy persisted stubbornly. As measurements improved on both sides, the uncertainty shrank, but the gap between the two values remained. Today, the distance ladder gives approximately 73 and the cosmic microwave background gives approximately 67, and the uncertainties on both measurements are small enough that this difference is statistically significant. The discrepancy now corresponds to roughly 5 sigma, meaning there is only about 1 in 3 million chance that this is a random statistical fluctuation. This is the Hubble tension. Two fundamentally different ways of measuring the universe's expansion rate give two different answers. Both methods appear to be correct within their own frameworks. Both have been scrutinized extensively by independent teams. Both continue to give the same results as more data accumulates. So what is going on? Why does the universe seem to be expanding at different rates, depending on how you measure it? The most conservative explanation is that there is still some systematic error we have not identified, despite years of searching. Perhaps the Cepheid calibrations have some subtle bias related to their stellar environments or chemical compositions. Perhaps there is a population of atypical type 1 supernovae contaminating the samples, explosions that look normal but are actually somewhat brighter or dimmer than average. Perhaps the cosmic microwave background analysis is affected by foreground contamination from our own galaxy or instrumental effects that have not been fully characterized. Scientists have searched extensively for such errors and have not found them. That does not mean they do not exist. Systematic errors are by definition effects you did not think to look for. But the failure to find any plausible systematic error despite years of effort suggests the discrepancy might be real. A more intriguing possibility is that the Hubble tension is telling us something genuine about the universe, that our standard cosmological model is incomplete or incorrect in some way that affects expansion measurements. The standard model of cosmology, lambda CDM, assumes that the universe contains ordinary matter, cold, dark matter, and dark energy described by a cosmological constant that does not change over time. It assumes that general relativity accurately describes gravity on all scales, from planets to the entire observable universe. It assumes that the universe is homogeneous and isotropic on large scales, meaning it looks roughly the same everywhere and in every direction when you average over large enough volumes. If any of these assumptions are wrong, it could affect how the universe expands and could potentially explain the Hubble tension. Some theorists have proposed that dark energy might not be constant over time. Perhaps the dark energy that drives cosmic acceleration was different in the early universe than it is today. Perhaps it has been slowly changing throughout cosmic history. A changing dark energy could make the universe expand at different rates at different epochs, potentially reconciling the cosmic microwave background and distance ladder measurements by having the expansion rate evolve in unexpected ways. Others have proposed modifications to the early universe specifically. Perhaps there was an additional form of energy that existed briefly in the first few 100,000 years and then decayed away. This early dark energy could have boosted the expansion rate during the cosmic microwave background era, affecting the inferred Hubble constant in ways that would bring it into agreement with local measurements. The energy would need to appear at just the right time and disappear completely, which seems fine-tuned, but such scenarios are being actively investigated. Some researchers have even suggested that general relativity might break down on cosmological scales, that gravity behaves differently across the vast distances between galaxies than it does in our solar system where we have tested it precisely. These ideas are more speculative and face significant theoretical challenges, but they illustrate the range of possibilities being considered. And this is where the James Webb Space Telescope enters the picture with its unprecedented capabilities. Webb has the ability to make independent measurements that could help resolve the Hubble tension, or at least constrain the possible explanations. Its infrared vision allows it to observe Cepheid variables with greater precision than any previous telescope. The infrared is particularly important because at these wavelengths, Cepheids are less affected by interstellar dust, which can dim their light unevenly and introduce errors in distance measurements. Dust is more transparent to infrared light than to visible light, so Webb sees through obscuring material that confused earlier observations. In 2023, the team that measures the Hubble constant using the distance ladder published new results incorporating Webb observations. They used Webb to observe Cepheid variables in several galaxies crucial for calibrating the distance ladder, including galaxies that host well-studied Type 1a supernovae. These galaxies serve as anchor points connecting the Cepheid and supernova distance scales. The results were striking. Webb's infrared observations reduced the scatter in the Cepheid measurements significantly. The brightness measurements were cleaner, more precise, less affected by contamination from nearby stars or dust obscuration. This showed that the distances calculated from these Cepheids were more accurate than ever before. More importantly, the Webb data confirmed the higher value of the Hubble constant, approximately 73 kilometers per second per megaparsec. This was not what many had hoped for. Some scientists had speculated that Hubble's Space Telescope measurements might be affected by crowding and blending, where the light from the Cepheid variable and light from nearby unresolved stars get mixed together in Hubble's images. This blending could potentially bias the brightness measurements, making Cephids appear brighter than they actually are, which would make them seem closer than they actually are, which would make the expansion rate seem faster than it actually is. Webb's sharper images in the infrared would resolve this blending and perhaps reveal that the true distances were different. The higher angular resolution would separate Cephids from their stellar neighbors, providing clean measurements free from contamination. But Webb showed that the Hubble Space Telescope measurements were essentially correct. The blending was minimal. The distances were accurate. The crowding that some had hoped would explain the tension simply was not significant enough to matter. The higher Hubble constant value appears to be real and is not an artifact of measurement problems that sharper imaging could solve. This deepens the mystery considerably. It rules out some of the simpler explanations for the tension and suggests that the discrepancy is not due to measurement errors in the distance ladder. Something about our understanding of the universe appears to be incomplete. Either the cosmic microwave background measurements are being interpreted incorrectly, or the local measurements are being affected by something we do not understand, or the universe genuinely behaves differently than our models predict. Webb's contributions to this debate are ongoing and will continue for years. The telescope is observing Cephids in additional galaxies, building up a larger sample with better precision and reducing any remaining statistical uncertainties. It is also observing other distance indicators that provide independent checks on the Cephid supernova method. The tip of the red giant branch is one such indicator. When stars like the Sun exhaust the hydrogen in their cores, they expand into red giants. As they continue to evolve, they reach a maximum brightness at what astronomers call the tip of the red giant branch, before undergoing helium, ignition, and becoming dimmer. This maximum brightness is nearly constant across different stellar populations, making it a useful standard candle independent of Cephids. Webb can measure this feature in distant galaxies with unprecedented precision. These new measurements will help constrain the possible explanations for the Hubble tension. If all methods that use objects in the nearby universe give a high value, and only the cosmic microwave background gives a low value, that would point toward new physics affecting the early universe. If different nearby methods give different values, that would suggest some methods have systematic errors we still do not understand. The pattern of agreement and disagreement across multiple independent techniques will eventually reveal the truth. The stakes are high. The Hubble constant is one of the most fundamental parameters of cosmology. It determines the age of the universe, the distances to all cosmic objects, and the fate of cosmic expansion. If we cannot measure it accurately, our entire understanding of the universe's history and ultimate destiny is uncertain. And if the tension is real, if it genuinely points toward new physics beyond our current models, then we might be on the verge of a major revolution in our understanding of the cosmos, comparable to the discovery of dark energy itself. Beyond the Hubble tension, Webb is also shedding new light on another deep mystery that has puzzled scientists for decades. The mystery of dark matter. Dark matter is one of the most important and least understood components of the universe. It makes up approximately 27% of the total energy content of the cosmos, far more than ordinary matter, which accounts for only about 5%. The rest, roughly 68%, is dark energy. We live in a universe dominated by components we do not understand. We know dark matter exists because of its gravitational effects, which are observed across many different scales. and contexts. Galaxies rotate too fast. If you measure how fast stars orbit in the outer regions of spiral galaxies, they are moving much faster than they should based on the gravitational pull of visible matter alone. The stars should fly off into intergalactic space. Something invisible is holding them in, providing additional gravitational attraction. Galaxy clusters are held together more tightly than visible matter alone could explain. When you add up all the hot gas and all the galaxies in a cluster and calculate the gravitational binding, it is not enough. The clusters should have flown apart billions of years ago, yet they remain bound, held together by invisible mass. The cosmic microwave background shows fluctuation patterns that only make sense if dark matter exists. The specific sizes and spacings of the temperature variations encode information about how matter clumped in the early universe. Without dark matter to provide additional gravitational scaffolding, the pattern would look different. The agreement between predictions and observations is precise. Gravitational lensing, where massive objects bend the light from more distant sources, reveals dark matter concentrations that have no visible counterpart. You can map where mass is located by how much it distorts the images of background galaxies. Often, this mass map does not align with where the visible galaxies are. Something massive and invisible is doing the lensing. But despite all this evidence that dark matter exists, we do not know what it actually is. Despite decades of experiments searching for dark matter particles in underground laboratories, in particle accelerators, and in space, none have been definitively detected. The leading candidates are weakly interacting massive particles, hypothetical particles that interact through gravity and the weak nuclear force, but not through electromagnetism or the strong force. Multiple experiments have searched for these particles and have not found them. Other candidates include axions, extremely light particles originally proposed to solve a different problem in particle physics. Primordial black holes that might have formed in the very early universe before stars existed, have also been proposed. Various exotic particles predicted by theories beyond the standard model of particle physics remain possibilities. What we do know is that dark matter behaves in specific ways that constrain what it can be. It interacts gravitationally but not electromagnetically. It does not emit light. It does not absorb light. It does not reflect light. It is completely transparent and invisible to all our telescopes, revealing itself only through the gravitational pull it exerts on things we can see. Dark matter clumps together over time through gravitational attraction, forming the cosmic scaffolding on which visible structures are built. In computer simulations of cosmic structure formation, dark matter collapses first, creating a web of filaments and dense nodes. Ordinary matter then falls into these dark matter concentrations, accumulating in the gravitational wells and forming galaxies. Without dark matter, galaxies like the Milky Way would not exist. The gravitational pull of ordinary matter alone was not sufficient to form structures as quickly as the universe produced them. The lambda CDM model makes specific predictions about how dark matter should be distributed throughout the universe. It predicts that galaxies should be surrounded by extended dark matter halos, spherical distributions of invisible matter that extend far beyond the visible stars and gas. It predicts that these halos should have specific density profiles, denser toward the center and becoming more diffuse with distance. It predicts a certain number of small subhalos, smaller concentrations of dark matter orbiting within the larger halos of big galaxies. Some of these predictions have been confirmed observationally. Others have proven more challenging. There has been ongoing tension between what simulations predict and what observations show, particularly on the smaller scales. Simulations predict more small satellite galaxies than we observe around the Milky Way. Simulations predict denser cores in dark matter halos than observations suggest. These discrepancies might reflect problems with our understanding of dark matter, or they might reflect complexities in how ordinary matter behaves that the simulations do not capture. Webb is now providing new data that bears on these questions with unprecedented clarity. Its ability to see faint, distant objects allows it to study the dark matter distributions around galaxies and clusters in ways that were previously impossible. One powerful way to study dark matter is through gravitational lensing. When light from a distant galaxy passes near a massive foreground object like a galaxy cluster, the light is bent by gravity. The amount of bending depends on the total mass along the line of sight, including both visible and dark matter. If the alignment is precise, the distant galaxy can appear as multiple images, stretched arcs, or even a complete ring around the foreground object. By analyzing the detailed patterns of this lensing, astronomers can map the distribution of mass in the foreground object, including its dark matter content. Webb's deep images reveal gravitational lensing in exquisite detail that previous telescopes could not achieve. The telescope has observed galaxy clusters where the lensing effects are so strong that distant galaxies appear as dramatically stretched arcs, wrapping around the cluster center. Some background galaxies are magnified by factors of tens or even hundreds, appearing far brighter than they would without the cosmic lens. By modeling these arcs with sophisticated software, astronomers can reconstruct the dark matter distribution in the lensing cluster. Some of these reconstructions have revealed unexpected features that challenge simple models. In certain clusters, the dark matter appears to be more concentrated than lambda CDM predictions suggest. The density profiles are steeper than simulations produce. In other clusters, the positions of individual galaxy-scale dark matter clumps do not quite match the positions of the visible galaxies they should be associated with. Small offsets appear that are difficult to explain if dark matter halos perfectly trace their host galaxies. These discrepancies could be statistical fluctuations, the result of small sample sizes and measurement uncertainties. They could be hints that our dark matter models need refinement. They could reflect complexities in the physics of galaxy clusters that are not captured in idealized simulations. Distinguishing between these possibilities requires more data and more careful analysis, both of which Webb is providing. Webb has also observed galaxies in the early universe that appear to have formed with unusual efficiency. As we discussed previously, some of these early galaxies are more massive than our models predicted possible. If stars formed more efficiently in the early universe, that might tell us something about the dark matter halos they formed within. Perhaps the halos were denser at early times than standard models predict. Perhaps they collapsed earlier, providing the gravitational wells for rapid star formation sooner than expected. The connection between early galaxy formation and dark matter properties is being actively explored. Some researchers have speculated about alternative dark matter models that could explain the observations Webb is returning. If dark matter particles had some weak self-interaction, colliding with each other occasionally rather than passing through each other like ghosts, they might clump differently than standard cold dark matter. The cores of halos might be less dense if dark matter particles could scatter off each other and redistribute their energy. This self-interacting dark matter is being explored theoretically and tested observationally. If there were multiple types of dark matter with different properties, different masses, or different interaction strengths, the mixture might behave in complex ways that a single component model cannot capture. If some fraction of dark matter were actually primordial black holes formed in the very early universe, that could affect structure formation in distinctive ways that observations might eventually reveal. These ideas are being actively explored as Webb continues to gather data. The telescope's observations of early galaxies, of gravitational lensing in clusters, and of galaxy dynamics in the local universe are all providing constraints that any successful dark matter model must satisfy. The web of evidence is tightening around the true nature of this mysterious component of the cosmos. There is also the profound question of what dark matter tells us about fundamental physics. Most dark matter candidates require physics beyond the standard model of particle physics. The standard model, which describes all known particles and forces except gravity, does not contain a suitable dark matter candidate. If we could identify what dark matter actually is, it would be a breakthrough not just for cosmology, but for particle physics as well. It would point toward new particles, new forces, perhaps even new structures in the laws of nature that we have not yet glimpsed. The search for dark matter continues on multiple fronts simultaneously. Underground detectors in deep mines try to catch rare interactions between dark matter particles and ordinary matter, looking for the tiny signals that would be produced if a dark matter particle occasionally bounced off an atomic nucleus. Particle accelerators attempt to create dark matter particles in high-energy collisions, looking for missing energy that would indicate invisible particles carrying energy away from the collision point. And telescopes like Webb search for the gravitational signatures of dark matter throughout the universe, mapping its distribution and testing predictions of different theoretical models. The universe that Webb is revealing is one where many of our assumptions need to be re-examined in light of new evidence. The Hubble tension suggests that either our measurements have subtle errors we have not identified, or our cosmological model is incomplete in some fundamental way. The dark matter distributions we observe sometimes match our predictions beautifully, and sometimes deviate in ways we cannot yet explain. The early galaxies are more mature than our models predicted they could be at such young cosmic ages. None of these findings necessarily mean that our fundamental physics is wrong. General relativity still works everywhere we can test it. The Big Bang model still explains the broad features of cosmic history. Lambda CDM still successfully describes the large-scale structure of the universe, the cosmic web of galaxies and voids that spans billions of light years. But the details matter. Science advances not just through grand theories, but through the accumulation of precise measurements that test those theories to their limits. Webb is providing measurements of unprecedented precision and scope. And where those measurements deviate from our expectations, we have the opportunity to learn something genuinely new about the cosmos. The universe is communicating with us through the data Webb collects. The Hubble tension is a message waiting to be decoded. The early massive galaxies are a message about how structure formed in the young universe. The dark matter distributions mapped through gravitational lensing are messages about the invisible scaffolding underlying all cosmic structure. Our task now is to understand what these messages are telling us about the nature of reality itself. While the headlines often focus on Webb's observations of the distant universe, galaxies forming impossibly early and cosmic tensions threatening to overturn cosmology, some of its most beautiful and scientifically profound discoveries are much closer to home. The telescope has turned its golden gaze toward the regions where stars are born, revealing the intricate processes of stellar and planetary formation with unprecedented clarity. What it is showing us is rewriting our understanding of how suns and worlds come into being, and by extension, how places like Earth become possible at all. Stars form in clouds of gas and dust, called molecular clouds. These clouds are vast structures, spanning tens or even hundreds of light years across, containing enough material to form thousands or millions of stars. They are incredibly cold by cosmic standards, typically only about 10 to 20 degrees above absolute zero. At these frigid temperatures, hydrogen exists primarily as molecules, two hydrogen atoms bonded together, rather than as individual atoms, hence the name molecular cloud. These clouds are also dark. The dust mixed throughout them blocks visible light so effectively that molecular clouds appear as black silhouettes against the background stars of the Milky Way. When you look at photographs of the night sky and see dark patches interrupting the starry background, you are often looking at molecular clouds, vast reservoirs of raw material waiting to be transformed into new stellar systems. The process of star formation begins when some region of a molecular cloud becomes dense enough for gravity to overcome the pressure that normally holds the cloud in equilibrium. Gas pressure pushes outward, resisting collapse. Gravity pulls inward, trying to compress the material. In most of the cloud, these forces balance, but if something disturbs this balance, if some region becomes dense enough that gravity gains the upper hand, collapse begins. This gravitational instability can be triggered by various events. The shock wave from a nearby supernova can compress the cloud, creating dense regions that begin to collapse. The passage of a spiral density wave as the cloud orbits through the Milky Way's spiral arms can have similar effects. The collision of two clouds can shock and compress gas. Radiation pressure from nearby hot stars can sculpt cloud edges, creating dense ridges where collapse initiates. Whatever the trigger, once gravity takes over, the process becomes self-reinforcing. The denser the region becomes, the stronger its gravitational pull, the faster material falls inward. As the material falls toward the center of the collapsing region, it heats up. Gravitational potential energy converts to thermal energy through compression. A protostar begins to form at the center, a dense concentration of hot gas that is not yet a true star, because nuclear fusion has not yet ignited in its core. Surrounding this protostar is a disk of material called a protoplanetary disk. This disk forms because the original cloud had some rotation. As material collapses, conservation of angular momentum causes it to spin faster, just as an ice skater spins faster when pulling in their arms. The spinning material cannot fall directly onto the protostar. Instead, it settles into a rotating disk. This disk is where planets will eventually form. The same material that is building the star also provides the raw ingredients for worlds that will orbit it. The disk contains gas, primarily hydrogen and helium, along with heavier elements in the form of dust grains, ice particles, and complex molecules. From this mixture, rocky planets like Earth and gas giants like Jupiter will eventually emerge. The protostar continues to grow as material from the disk spirals inward and falls onto it. This accretion process can be violent. Material does not fall smoothly, but arrives in bursts and streams. Jets of gas shoot outward from the protostar's poles, perpendicular to the disk, carrying away angular momentum and allowing accretion to continue. These jets can extend for light years, plowing into the surrounding cloud and creating glowing shock waves where they collide with ambient gas. At some point, when the core of the protostar reaches temperatures of approximately 10 million degrees Celsius, hydrogen fusion ignites. Protons begin fusing into helium nuclei, releasing enormous energy that stabilizes the star against further collapse. A true star is born, taking its place on what astronomers call the main sequence, where it will spend most of its life steadily converting hydrogen to helium. The remaining disk material faces several possible fates. Some will form planets, coalescing through processes we are still working to understand. Some will be blown away by the star's radiation and stellar winds, dispersing back into interstellar space. Some will fall onto the star, adding final increments to its mass. Within a few million years, the disk will be gone, leaving behind whatever planetary system has managed to form. This basic picture of star formation has been understood for decades, assembled through theoretical modeling, computer simulations, and observations at various wavelengths. But the details have always been murky, quite literally. Star-forming regions are filled with dust that blocks visible light almost completely. We knew stars formed inside these dusty cocoons, but we could not see through the obscuring material to watch the process happen. It was like trying to understand human development by looking only at adults, never being able to observe children. Webb changes everything. Infrared light penetrates dust far better than visible light. The longer wavelength infrared photons slip past dust grains that would block shorter wavelength visible photons. With its infrared vision, Webb can peer through the dusty veils that shroud stellar nurseries, revealing the protostars, disks, and jets that were previously hidden from view. For the first time, we can watch star formation as it actually happens. One of the most spectacular early images from Webb showed the Carina Nebula, a massive star-forming region approximately 7,600 light-years from Earth, in the southern constellation Carina. The image, released in July 2022 as part of Webb's first set of scientific observations, showed what appeared to be a cosmic cliff, a towering wall of gas and dust being sculpted by the radiation from young, hot stars above the frame. What looked like a craggy mountain range, complete with peaks and valleys and dramatic lighting, was actually the edge of a giant cavity carved into the nebula by stellar winds and ultraviolet radiation. The hot stars above the cliff are blasting away the gas, eroding the cloud like water eroding a shoreline. The cliff face marks the boundary between gas that has been cleared and gas that remains. The visual effect is stunning. A landscape of cosmic scale rendered in infrared light. But the true revelation came from looking at the details within this panorama. Throughout the image, Webb revealed dozens of previously unseen protostars embedded in the dusty ridges. These young objects, still gathering material from their surroundings, appeared as bright points of infrared light, shining through the obscuring dust. Visible light telescopes had looked at this same region countless times and seen only darkness. Webb revealed that the darkness was actually teeming with stellar activity. Some of these protostars were driving jets of material perpendicular to their disks, clearing pathways through the surrounding gas. These jets appeared as narrow streaks extending away from the protostars. glowing where they heated the ambient material. The jets trace the rotation axes of the protostellar systems, pointing perpendicular to the disks we cannot directly resolve at this distance. These jets, called Herbig-Haro objects after the astronomers who first studied them, are one of the most dramatic features of star formation. As material falls onto a young star through its disk, some of that material gets redirected by magnetic fields and shoots outward at speeds of hundreds of kilometers per second. The physics is complex, involving the interaction of gravity, rotation, and magnetic fields in ways that simulations are still working to fully capture. But the result is spectacular. Narrow beams of gas punching through the surrounding cloud like cosmic blowtorches. When these jets collide with the surrounding gas, they create shock waves that compress and heat the material, causing it to glow at specific wavelengths. Webb's images revealed jets that had never been seen before at any wavelength, showing how common this process is during stellar birth. Nearly every protostar drives jets at some point in its formation, making them a fundamental part of how stars assemble themselves. The telescope has also observed the Orion Nebula, perhaps the most famous star-forming region in the sky, and certainly the most studied. Located only about 1,340 light-years from Earth in the sword of the constellation Orion, the Orion Nebula is close enough that Webb can resolve individual protoplanetary disks around young stars. This proximity makes Orion an invaluable laboratory for studying the details of star and planet formation. These disks appear in Webb's images in multiple ways depending on their orientation and illumination. Some appear as dark silhouettes against the bright background of the nebula, their dust blocking the light from behind. These are seen edge-on, their disk nature obvious from their flattened shapes. Others appear as glowing structures illuminated by nearby hot stars, their dust scattering and re-emitting infrared light. Still others are detected primarily through the infrared emission from the warm dust they contain. In some cases, Webb has observed disks with gaps and rings, concentric structures that suggest planets may already be forming within them. According to theoretical models, as a planet grows larger within a disk, its gravity disturbs the surrounding material. The planet clears material from its orbital path, creating a gap. If multiple planets are forming, multiple gaps appear, producing the ringed structures that Webb and other telescopes have observed in numerous protoplanetary disks. These observations are providing crucial tests of planet formation theories that have been debated for decades. Astronomers have proposed two main mechanisms for how planets form, and the truth may involve both operating under different circumstances. The leading theory, called core accretion, suggests that planets begin as small rocky cores that grow by accumulating solid particles in the disk. Dust grains stick together when they collide, building larger and larger aggregates. Eventually, kilometer-scale bodies called planetesimals form, and these gravitationally attract additional material, growing into protoplanets. Once a core becomes massive enough, roughly 10 to 15 times Earth's mass, it can gravitationally capture gas from the surrounding disk, potentially becoming a gas giant like Jupiter or Saturn. But core accretion has difficulties explaining how giant planets can form quickly enough. Protoplanetary disks do not last forever. After a few million years, the central star's radiation and stellar winds disperse the remaining gas. Observations show that most disks are essentially gone within 10 million years. If giant planets cannot accumulate their massive atmospheres before the gas disperses, they cannot form through this mechanism. An alternative theory, called disk instability, suggests that giant planets can form directly from the gravitational collapse of unstable regions in the disk itself. If part of the disk becomes dense enough and cools enough, gravity can cause it to fragment and collapse into a planet-mass object almost instantaneously on astronomical timescales. This process could form giant planets in thousands of years rather than millions, easily beating the deadline imposed by disk dispersal. Webb's observations of protoplanetary disks are helping to distinguish between these theories by revealing the conditions within disks at various stages of evolution. By studying the structures in disks, the compositions of the gas and dust, the temperatures at different distances from the star, and the properties of any young planets detected within them, astronomers are constraining which mechanisms actually operate and under what circumstances. And Webb is not limiting its observations to disks around stars similar to the Sun. It is also examining disks around very different kinds of stars, including red dwarfs, the most common type of star in the galaxy. Red dwarfs are small, cool stars with masses between roughly 8 and 50% of the Sun's mass. They are far less luminous than the Sun, sometimes by factors of thousands. What they lack in brightness, they make up in numbers. Roughly 70% of all stars in the Milky Way are red dwarfs. If planets around red dwarfs are common, then most planets in the galaxy orbit these small, cool stars. For a long time, astronomers thought red dwarfs might be poor hosts for planets, particularly habitable planets. Their lower luminosity means they're habitable zones. The regions where liquid water could exist on a planet's surface are much closer to the star than Earth is to the Sun. A planet in the habitable zone of a typical red dwarf might orbit at only a few percent of the Earth-Sun distance, completing an orbit in days or weeks rather than a year. Planets in such close orbits face several challenges. They would likely be tidally locked, always showing the same face to their star, just as the Moon always shows the same face to Earth. One hemisphere would experience permanent day, while the other experienced permanent night. The climate implications of such a configuration are complex and still debated. Close orbiting planets would also be subject to intense stellar activity. Red dwarfs, particularly young ones, produce frequent and powerful flares, sudden releases of magnetic energy that can temporarily multiply the star's brightness. These flares emit intense ultraviolet and X-ray radiation that could strip away planetary atmospheres over time. Whether planets around red dwarfs can retain atmospheres and surface water remains an open question. Despite these concerns, observations over the past 2 decades have shown that planets around red dwarfs are extremely common. Many of the most exciting exoplanet discoveries have been around red dwarfs, systems that will feature prominently in Webb's search for potentially habitable worlds. The Proxima Centauri system, the nearest star system to the Sun, hosts at least one and possibly more planets around its red dwarf star. Webb is observing the disks around young red dwarfs to understand how planets form in these environments. Are the disks similar in composition and structure to those around solar-type stars? Do they evolve similarly? Do they produce the same kinds of planets through the same mechanisms? The answers will help us understand just how common potentially habitable worlds might be throughout the galaxy. Perhaps the most exciting aspect of Webb's observations of star-forming regions is what they reveal about chemistry. Stars and planets form from the same material the gas and dust of molecular clouds. The composition of this material, what molecules it contains, how those molecules are distributed within the cloud and within individual protoplanetary disks, determines what kinds of planets can form and what their compositions will be. Webb's spectrographs can analyze the light from star-forming regions and determine what molecules are present with unprecedented precision. When infrared light passes through or reflects off gas and dust, specific molecules absorb or emit light at characteristic wavelengths. By measuring which wavelengths are affected, astronomers can identify the molecules responsible and estimate their abundances. In some of Webb's first observations, the telescope detected water, carbon dioxide, carbon monoxide, methane, and various organic molecules in the disks around young stars. Some of these detections confirmed previous observations from other telescopes, validating both the older results and Webb's calibrations. Others were surprising, revealing molecules that were more or less abundant than theoretical models had predicted. Each detection adds to our inventory of the chemical ingredients available for building planets. One particularly important detection involves water ice. Water is essential for life as we know it, and understanding how water is distributed in protoplanetary disks tells us about how planets acquire their water. Did Earth get its water from asteroids and comets that formed in the outer solar system and later impacted our planet? Or did water exist in the inner disk where Earth formed? The distribution of water in disks at various stages of evolution provides clues. Webb has observed water ice in multiple disks, sometimes in locations closer to the star than models predicted. The boundary beyond which water ice can exist, called the snow line, depends on the disk's temperature structure. Water ice inside this line sublimates into vapor. Water ice outside this line remains frozen. But disks are not simple, and the snow line can shift over time as the disk evolves. Webb's observations are mapping where water ice actually exists, compared to where simple models place it. Webb has also detected complex organic molecules in star-forming regions. Molecules containing carbon atoms bonded to hydrogen, oxygen, nitrogen, and other elements in intricate arrangements. These are the precursors to the molecules of life, the building blocks from which amino acids, proteins, and nucleic acids could eventually form. Finding these molecules in the environments where planets are born suggests that the raw materials for life might be distributed throughout the galaxy wherever stars and planets form. But Webb's observations of stellar births represent only half the cosmic story of stellar evolution. The telescope is also observing stellar deaths, the supernova remnants and planetary nebulae left behind when stars end their lives. And these observations are revealing the crucial role that dying stars play in seeding the universe with the elements necessary for planets and life. When a massive star, one with more than roughly 8 times the mass of the Sun, exhausts its nuclear fuel, its core collapses catastrophically. Throughout its life, the star has been fusing lighter elements into heavier ones, hydrogen into helium, helium into carbon, carbon into heavier elements still. This fusion releases energy that supports the star against its own gravity. But when the core consists primarily of iron, fusion can no longer release energy. It would actually require energy to fuse iron into heavier elements. The energy source that held the star up for millions of years suddenly fails. The core collapses in a fraction of a second, compressing from a size comparable to Earth to a size comparable to a city. The outer layers of the star, no longer supported, fall inward and then rebound off the suddenly rigid core. A shockwave races outward through the star, tearing it apart in a supernova explosion. For a few weeks, the dying star can outshine an entire galaxy containing hundreds of billions of stars. The explosion throws the star's outer layers into space at speeds of thousands of kilometers per second. These expanding shells of gas and dust become supernova remnants, structures that can persist for tens of thousands of years as they expand and slowly merge with the surrounding interstellar medium. During this time, they remain visible at various wavelengths, glowing as the expanding shockwave heats and compresses the gas it encounters. Supernova remnants are important for several reasons that directly connect to our own existence. They are the primary source of heavy elements in the universe. Elements like iron, nickel, gold, platinum, and uranium are forged in the extreme conditions of the supernova explosion itself, created in the seconds during the collapse and subsequent rebound when temperatures and densities reach values found nowhere else. These elements are then dispersed into space by the explosion, mixing with existing interstellar gas and eventually becoming incorporated into future generations of stars and planets. Every atom of iron in your blood was created in a supernova explosion billions of years ago. The calcium in your bones, the phosphorus in your DNA, the copper in your nerves, all were forged in dying stars and scattered across space to eventually become part of the molecular cloud from which our solar system formed. We are quite literally made of stellar debris. Studying supernova remnants means studying the cosmic factories that created the elements that make up our world and our bodies. Webb has observed several supernova remnants, revealing details that were invisible to previous telescopes operating at other wavelengths. The infrared light that Webb detects is produced by dust within the remnants, dust that formed in the aftermath of the explosion from the heavy elements it created. This dust is now being heated by the expanding shockwave and by radiation from surrounding stars, causing it to glow at infrared wavelengths. One of Webb's most striking images shows Cassiopeia A, the remnant of a supernova that exploded approximately 340 years ago, as seen from Earth. The light from this explosion should have been visible in the night sky in the late 1600s, but no definitive historical records of its observation have been identified. Today, the remnant spans about 10 light years across and is one of the brightest radio sources in the sky, though it is relatively faint in visible light. In Webb's infrared images, Cassiopeia A transforms into something spectacular. The remnant glows with intricate filaments and knots of material, delicate structures tracing the shockwave as it plows through the surrounding interstellar medium. Different wavelengths of infrared light trace different chemical elements, showing how the explosion distributes silicon, sulfur, argon, neon, and other elements across a vast bubble of space. The distribution is not uniform, but clumpy and asymmetric, recording the chaotic dynamics of the explosion itself. One surprising finding was the detection of unusually hot material near the center of the remnant, a feature that previous observations had not clearly revealed. This central emission might arise from the neutron star or other compact object left behind by the explosion, though the interpretation remains uncertain and subject to ongoing analysis. Webb's observations are providing new constraints on what remains at the heart of this cosmic catastrophe. For lower mass stars like the Sun, death comes more gently. These stars do not have enough mass to trigger core collapse and supernova explosion. Instead, They swell into red giants as they exhaust the hydrogen in their cores, eventually shedding their outer layers through stellar winds, while the core contracts into a dense remnant called a white dwarf. The ejected material forms a planetary nebula, often displaying beautiful symmetric patterns that have made these objects favorites of astronomical imaging. Despite their name, planetary nebulae have nothing to do with planets. The name arose in the 18th century when early telescopic observers thought these round, fuzzy objects resembled the disks of distant planets. We now know they are shells of gas expelled by dying stars, illuminated by the hot central remnant. Webb has observed several planetary nebulae revealing structures that were invisible at other wavelengths. The Southern Ring Nebula, observed as part of Webb's first image release in July 2022, shows two stars at its center. One is the white dwarf that created the nebula, now incredibly hot and small. The other is a companion star that likely influenced how the nebula was shaped through gravitational interaction. The complex patterns visible in the nebula trace the mass loss history of the dying star over its final thousands of years. Multiple shells of material are visible, separated by gaps that indicate pauses in the mass ejection. Some features suggest that material was expelled preferentially in certain directions rather than uniformly in all directions. Understanding these patterns tells us about the final stages of stellar evolution and provides a preview of how stars like our Sun will eventually end their lives. Webb has also made groundbreaking observations of exoplanet atmospheres, extending our understanding of worlds beyond our solar system. By watching as an exoplanet passes in front of its host star, a phenomenon called a transit, astronomers can detect the tiny amount of starlight that filters through the planet's atmosphere. Different molecules absorb light at different characteristic wavelengths. By analyzing which wavelengths are dimmed during transit, scientists can determine what the atmosphere contains. This technique, called transmission spectroscopy, has been used for years with Hubble and ground-based telescopes. But Webb's infrared sensitivity and spectroscopic power have elevated it to unprecedented precision. Molecules that absorb primarily at infrared wavelengths, invisible to visible light telescopes, are now accessible. In August 2022, Webb made the first definitive detection of carbon dioxide in an exoplanet atmosphere. The planet, designated WASP-39b, is a gas giant with a radius approximately 1.3 times that of Jupiter, but only about 1/4 of Jupiter's mass, making it a puffy, low-density world orbiting extremely close to its star and completing an orbit in only about 4 days. The planet's atmosphere is heated to over 800 degrees Celsius by its proximity to its star, a world utterly unlike anything in our solar system. Webb's observations showed a clear spectroscopic signature of carbon dioxide absorption at precisely the wavelengths where this molecule is expected to absorb light. The detection was unambiguous, a definitive identification that previous telescopes had been unable to achieve despite attempts. This was more than just a technical milestone. Carbon dioxide is an important molecule for understanding planetary atmospheres across a wide range of conditions. It is a potent greenhouse gas that can significantly affect a planet's temperature. Detecting it and measuring how much is present provides information about the planet's atmospheric chemistry, its formation history, and its climate. Carbon dioxide abundance depends on the interplay of geological, chemical, and potentially biological processes, making it a key diagnostic for understanding alien worlds. Since that first detection, Webb has observed the atmospheres of numerous exoplanets, building a growing database of atmospheric compositions. It has detected water vapor, methane, carbon monoxide, sulfur dioxide, and various other molecules. Some detections match theoretical predictions, confirming that our models of atmospheric chemistry have merit. Others were surprises, revealing atmospheric compositions different from what models suggested, pointing toward chemistry we do not yet fully understand. One of the most exciting frontiers is the search for biosignatures, molecular signatures in planetary atmospheres that might indicate the presence of life. On Earth, oxygen and ozone are largely products of photosynthesis by plants and cyanobacteria. Methane is produced by both geological processes and living organisms. Certain combinations of gases that would not coexist in chemical equilibrium unless something continuously replenished them could indicate biological activity. Webb cannot yet detect these biosignatures on truly Earth-like planets, small rocky worlds orbiting sun-like stars at Earth-like distances. Those planets are too small and their atmospheric signals too weak relative to their bright host stars. But Webb can study the atmospheres of somewhat larger planets orbiting smaller, dimmer red dwarf stars, where the planet-to-star size ratio is more favorable and transits are more frequent. The TRAPPIST-1 system remains a prime target. Its 7 Earth-sized planets orbit a red dwarf star, only about 40 light-years away. 3 of those planets orbit within the habitable zone, where liquid water could potentially exist on their surfaces. Webb has observed these planets repeatedly, searching for signs of atmospheres. If Webb detects an atmosphere on one of these potentially habitable worlds, it will represent a major scientific milestone, regardless of the atmosphere's composition. And if that atmosphere contained unexpected molecules, combinations that might hint at biological activity, it would rank among the most profound discoveries in human history. We are not there yet. The observations are difficult, the signals are small, and interpretations are uncertain. But Webb is providing our first realistic opportunity to search for signs of life on worlds orbiting other stars. The theme connecting all these observations, from star-forming nebulae to dying stars to exoplanet atmospheres, is cosmic chemistry. The universe is a vast chemical factory operating over billions of years. Stars are born from elements forged in previous stellar generations. They create new elements through fusion during their lives, and through explosive nucleosynthesis at their deaths. Planets form from this chemically enriched material, incorporating the full periodic table into their compositions. And on at least one planet, those chemicals combine through processes we still do not fully understand to create life. Webb is providing an unprecedented view of cosmic chemistry at every stage of this grand cycle. We are seeing the molecules in the clouds where stars form, the raw ingredients for planetary systems. We are seeing the elements created in supernova explosions, the heavy nuclei that make rocky planets possible. We are seeing the compositions of planetary atmospheres around other stars, the chemical environments where life might or might not arise. Each observation adds to our understanding of how the universe creates the conditions for complexity and potentially for life. In the heart of nearly every large galaxy lies a monster. Supermassive black holes, with masses ranging from millions to billions of times that of the Sun, lurk at the centers of galaxies throughout the universe. For decades, we have known they exist. We have measured their masses through the motions of stars and gas swirling around them. We have observed the brilliant quasars powered by material falling into them, some of the most luminous objects in the entire cosmos. But the James Webb Space Telescope is revealing something unexpected about these cosmic behemoths. They grew too fast. According to our understanding of how black holes form and grow, the supermassive black holes we observe in the early universe should not be as massive as they are. Not so soon after the Big Bang. Not when the universe was still in its infancy. And Webb is finding more of these impossibly massive early black holes than anyone predicted, adding another puzzle to the growing list of cosmic mysteries the telescope has uncovered. To understand why this is surprising, we need to examine how black holes are supposed to grow according to established physics. A black hole increases its mass by consuming material, gas, dust, stars, anything that ventures too close to escape its gravitational grip. When material falls toward a black hole, it does not plunge straight in like water down a drain. Instead, it spirals inward, forming a hot, luminous structure called an accretion disk. This disk can radiate enormous amounts of energy as gravitational potential energy converts to heat and light, sometimes outshining the entire galaxy surrounding the black hole by factors of hundreds or thousands. But there is a fundamental limit to how fast a black hole can grow through this process. As material falls inward and heats up, it produces intense radiation. That radiation exerts pressure, pushing outward against the infalling material. If the black hole tries to consume material too quickly, the radiation pressure becomes so strong that it pushes the incoming material away, effectively shutting off the flow of fuel. This balance point where radiation pressure equals gravitational attraction is called the Eddington limit, after the British astrophysicist Arthur Eddington, who first described it. At the Eddington limit, a black hole roughly doubles its mass every 40 to 50 million years. That sounds impressively fast by human standards, but it is not fast enough to explain what we observe in the distant universe. Consider the arithmetic. If you start with a stellar mass black hole, one formed from the gravitational collapse of a massive star with perhaps 10 to 100 times the mass of the Sun, and grow it continuously at the Eddington limit for the entire 13.8 billion year history of the universe, you would end up with a black hole of roughly 1 billion solar masses. That seems adequate until you consider what astronomers have actually observed. We have detected black holes far more massive than 1 billion solar masses, and we have detected them when the universe was less than 1 billion years old. Some of the earliest known quasars, objects we observe as they existed when the universe was only 700 or 800 million years old, contain black holes with masses of several billion solar masses. The math simply does not work. There was not enough time to grow black holes this massive from stellar mass seeds, even if they accreted material at the maximum possible rate without interruption. This problem existed before Webb launched. Astronomers have puzzled over the existence of billion solar mass black holes in the early universe for years. But Webb is making the problem considerably worse by revealing the scope of rapid black hole growth in the young cosmos. Webb has discovered numerous active galactic nuclei at extremely high redshifts, revealing accreting black holes in the early universe that are surprisingly massive for their cosmic epoch. Some of these black holes appear to have masses of millions or tens of millions of solar masses in galaxies that existed just a few 100 million years after the Big Bang. At times when our models suggest black, holes should still be relatively small. Now, These masses are smaller than the multi-billion solar mass monsters powering the brightest early quasars, but they are still too big. There simply was not enough time to grow black holes this massive from normal stellar mass seeds, even under the most optimistic assumptions about continuous maximum rate accretion. Something about black hole formation and growth in the early universe worked differently than our standard models predict. Moreover, Webb is finding that these early black holes appear to be more common than expected. The number of moderately luminous active galactic nuclei in the early universe seems to exceed predictions from theoretical models. This is not just a few anomalous objects that might be explained as statistical outliers. This is a population of early black holes that our models failed to anticipate. The early universe was apparently more efficient at making and growing black holes than we understood. Several explanations have been proposed to account for this discrepancy, and the truth may involve some combination of mechanisms operating together. One possibility is that the first black holes were not stellar mass at all. Perhaps they formed directly from the collapse of massive primordial gas clouds, creating seed black holes that were already tens of thousands or even hundreds of thousands of solar masses from the beginning. These direct collapse black holes would have an enormous head start on growing to supermassive sizes. Instead of starting at 10 solar masses and needing to grow by factors of hundreds of millions, they would start at 100,000 solar masses and need to grow by factors of only tens of thousands. The same Eddington limited growth that cannot explain billion solar mass black holes from stellar seeds might work perfectly well from these more massive starting points. The physics of direct collapse is plausible under certain conditions. In the early universe, before heavy elements had been synthesized and dispersed by the first generations of stars, gas clouds could not cool efficiently. Without heavy elements to radiate away thermal energy, collapsing clouds would remain hot, and hot gas resists fragmentation into small clumps. Instead of breaking up into many small protostars, a massive primordial cloud might collapse as a single unit, forming one enormous object that quickly becomes a black hole. This scenario requires specific conditions, but those conditions may have been common in the early universe. Another possibility is that black holes in the early universe somehow exceeded the Eddington limit for extended periods. Perhaps the geometry of the accretion flow was different from what we typically model, allowing more material to fall in while radiation escaped along different paths. Perhaps there were episodes of super Eddington accretion, brief periods when black holes consumed material at rates far exceeding the nominal limit, before settling back into more moderate growth. Super Eddington accretion is theoretically possible under certain conditions, and even brief episodes could significantly boost the final black hole mass. A third possibility involves black hole mergers. When galaxies collide, which happened frequently in the crowded early universe, the black holes at their centers eventually spiral together and merge. The resulting black hole instantly has the combined mass of both progenitors. Enough mergers, happening fast enough, could build up supermassive black holes more quickly than accretion alone would allow. This scenario requires that galaxy mergers were common in the early universe and that the black holes within merging galaxies could find each other and combine efficiently, neither of which is guaranteed, but both of which are plausible. Webb's observations are providing data to test these scenarios against reality. By measuring the properties of early black holes, their masses, their accretion rates, their relationship to their host galaxies, astronomers can constrain which growth mechanisms are physically plausible and which can be ruled out. One particularly intriguing finding involves the relationship between black holes and their host galaxies. In the nearby universe, there exists a remarkably tight correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge, the dense central concentration of stars that most large galaxies possess. Bigger galaxies consistently have bigger black holes, and the ratio is surprisingly constant across a wide range of galaxy masses and types. This relationship, known as the M-sigma relation or the black hole mass-bulge mass relation, implies that black holes and galaxies grow together in some coordinated way, regulating each other's development through feedback processes. When a black hole accretes vigorously, it releases enormous energy that can heat the surrounding gas, preventing that gas from cooling and forming new stars. This suppresses star formation in the host galaxy. Conversely, when stars form and massive ones explode as supernovae, the resulting shock waves can drive gas toward the galactic center, feeding the black hole. This cosmic dance of mutual regulation keeps black holes and galaxies in lockstep over billions of years. But Webb's early observations suggest that this orderly relationship might not hold in the early universe. Some of the early galaxies with active black holes appear to have black holes that are overmassive relative to their stellar content. The black holes are bigger than you would expect, given the relatively modest size of their host galaxies. The ratio is off, sometimes by factors of 10 or more. This could mean that black holes grew first, reaching substantial masses before their host galaxies had time to fully assemble their stellar populations. The black holes would then sit at the centers of relatively small galaxies, waiting for their hosts to catch up over subsequent billions of years of star formation. It could mean that the feedback processes work differently at early cosmic times, perhaps with black holes dominating the energy budget before galaxies establish the regulatory mechanisms we see operating today. It could also mean that our measurements are biased in some way, that we are systematically overestimating black hole masses or underestimating galaxy masses in these distant objects. Whatever the explanation, the finding tells us that the coevolution of black holes and galaxies, something that seems so orderly and well regulated in the nearby universe, had a more chaotic and less balanced beginning. The early universe operated under different rules, and its black holes didn't follow the relationships we have come to expect from studying cosmic structure in the present epoch. Beyond supermassive black holes, Webb is observing other strange objects that challenge our understanding. One category that has generated particular interest is the so-called little red dots, compact red sources that Webb has found in surprising abundance in the early universe. These objects earned their informal name from their appearance in Webb's images. They are red because their light has been shifted to longer wavelengths by the expansion of the universe, and possibly also because they contain substantial amounts of dust that reddens transmitted light. They are little because they appear unresolved or barely resolved even in Webb's sharp images, meaning they are remarkably compact for their luminosity. When astronomers first identified these little red dots in Webb's deep field observations, they were uncertain what they were looking at. Were they compact galaxies undergoing intense star formation? Were they active galactic nuclei powered by accreting black holes? Were they some previously unknown class of object that did not fit neatly into existing categories? The red color and compact size were consistent with multiple interpretations. Spectroscopic observations with Webb have helped clarify the picture, though questions remain. Many of the little red dots show emission lines characteristic of active galactic nuclei, indicating they harbor accreting black holes at their centers. The specific patterns of emission reveal gas moving at high velocities, heated to extreme temperatures by the energy released as matter spirals into a black hole. Some little red dots show signatures of both young stellar populations and active nuclei simultaneously. They might represent a phase of early galaxy evolution where intense star formation and vigorous black hole growth occur together, perhaps triggered by the same processes and fed by the same reservoirs of gas. But puzzles persist. Why are there so many of these objects in the early universe? Why do they seem to be more common than theoretical models predicted? Are they a brief but universal phase that most early galaxies pass through during their development, or are they a special population produced by unusual circumstances? The answers remain unclear, and Webb continues to observe these enigmatic objects in search of understanding. These questions connect to the broader mystery of the early universe that has emerged from Webb's observations. Everything seems to happen faster than expected. Galaxies assemble more quickly. Stars form more efficiently. Black holes grow to larger masses in shorter times. The early universe was apparently a more dynamic and productive environment than our models anticipated, generating complex structures with surprising speed. Webb has also observed gravitational lensing phenomena in unprecedented detail, revealing aspects of distant objects that would otherwise be impossible to study. When light from a distant source passes near a massive foreground object like a galaxy cluster, the gravity of the foreground mass bends the light's path. This bending can create multiple images of the background source, stretch it into dramatic arcs, and magnify it to many times its unlensed brightness. In some cases, the alignment between background source, foreground lens, and our line of sight is so precise that extraordinary magnifications occur. Individual stars and galaxies billions of light years away can be separately detected, something that would normally be completely impossible at such distances. This phenomenon, called extreme magnification or caustic crossing, occurs when a background star passes near a caustic, a line in the lens plane where magnification theoretically becomes infinite. One such star, nicknamed Earendel after a character in Tolkien's mythology, was discovered in Hubble Space Telescope images and subsequently observed with Webb in greater detail. Earendel is a massive star in a galaxy approximately 12.9 billion light-years away, seen as it existed when the universe was less than 1 billion years old. It is among the most distant individual stars ever detected, visible only because gravitational lensing has magnified its light by factors of thousands. Webb's observations of Earendel and similar highly magnified stars provide unique insights into the properties of stellar populations in the early universe. Are these ancient stars fundamentally different from stars forming today? Do they have different masses, different compositions, different lifespans? The answers inform our understanding of how the first generations of stars formed and how they contributed to the chemical enrichment of the cosmos. These magnified views offer windows into stellar physics at epochs when direct observation would otherwise be impossible. Webb has also turned its attention to unexpected objects much closer to home. Within our own solar system, the telescope has observed planets, moons, asteroids, and comets, often revealing features that ground-based telescopes and previous space missions could not detect. Observations of Jupiter showed the giant planet's auroras in stunning detail, revealing the complex magnetic interactions between Jupiter and its environment. The auroras appeared as glowing regions near the planet's poles, tracing the magnetic field lines along which charged particles from the Sun and from Jupiter's volcanic moon Io spiral into the atmosphere. Webb's infrared vision also revealed previously unknown features in Jupiter's atmosphere, subtle structures in the cloud bands that visible light observations had missed. Images of Saturn's largest moon Titan revealed complex cloud patterns in its thick nitrogen-methane atmosphere, along with reflections from the hydrocarbon lakes that dot its surface. Titan is the only moon in the solar system with a substantial atmosphere and the only body other than Earth known to have stable liquid on its surface, though the liquid is methane and ethane rather than water. Understanding Titan's atmospheric chemistry and surface features informs our understanding of prebiotic chemistry and the conditions that might lead to life under different circumstances than those on Earth. One notable observation involved the DART mission, which deliberately crashed a spacecraft into the small asteroid Dimorphos in September 2022 to test whether such an impact could alter an asteroid's trajectory. This was humanity's first planetary defense test, an experiment in whether we could deflect a potentially hazardous asteroid if one were ever discovered on a collision course with Earth. Webb observed the impact from its vantage point 1.5 million kilometers from Earth, capturing the plume of debris ejected from the asteroid. The observations helped scientists understand how much material was released, how it dispersed into space, and what the impact revealed about the asteroid's composition and structure. These solar system observations might seem modest compared to Webb's cosmological discoveries, but they showcase the telescope's remarkable versatility. Webb is not exclusively a deep space observatory. It is a general-purpose infrared telescope that can contribute to nearly every area of astronomical research, from objects in our cosmic backyard to the most distant structures in the observable universe. As we look toward the future, what can we expect from Webb and from astronomy as a whole? Webb was designed to operate for at least 5 years, with a goal of 10 years and the possibility of extending even longer if its components remain functional. The telescope carries enough fuel for approximately 20 years of station keeping at its orbit around the L2 point. So fuel will not be the limiting factor. The ultimate lifetime will depend on how well the instruments continue to function in the harsh environment of space. That represents a substantial amount of remaining observing time, and astronomers around the world have ambitious plans for using it. Observing proposals are submitted competitively, with review panels evaluating which programs will produce the most valuable science. The demand for Webb time far exceeds the supply, a testament to how many important questions the telescope can address. The early universe will remain a major scientific focus. The observations so far have raised more questions than they have answered. How did the first galaxies form so quickly? How did supermassive black holes grow so fast? What physical processes operated differently in the early cosmos compared to today? Webb will continue probing these questions, pushing to ever higher redshifts, studying ever fainter and smaller objects at the edge of detectability. Exoplanet science will expand dramatically as Webb accumulates more observations of planetary atmospheres. The telescope has begun to characterize the atmospheric compositions of various worlds, from hot gas giants to smaller planets in potentially habitable zones. But each individual planet typically requires many hours of observation to build up adequate signal. Longer observations of more planets will construct a catalogue of atmospheric compositions, spanning diverse planetary types, identifying patterns that reveal common processes and outliers that point toward unusual chemistry or perhaps something more intriguing. Stellar astronomy will benefit from Webb's unique capabilities for years to come. The processes of star and planet formation will be studied in dozens of different environments, molecular clouds of various densities and compositions, star-forming regions in the Milky Way and in nearby galaxies, disks around stars of different masses and ages. This accumulating data will build up a statistical picture of how these processes work under different conditions, testing theoretical models against diverse observations. But Webb is just one telescope, however remarkable. The future of astronomy involves many facilities working together, each contributing unique capabilities to the collective enterprise of understanding the universe. On the ground, a new generation of extremely large telescopes is under construction. The extremely large telescope being built by the European Southern Observatory in the Atacama Desert of Chile will have a primary mirror 39 meters across, far larger than any existing optical telescope. The Giant Magellan Telescope and the 30-meter telescope are also in various stages of development. These facilities will achieve angular resolution even sharper than Webb's through the use of adaptive optic systems that correct for atmospheric turbulence in real time. They will observe primarily at visible and near-infrared wavelengths, complementing Webb's strengths in the thermal infrared. In space, future missions are being planned and developed to succeed Webb and expand upon its achievements. The Nancy Grace Roman Space Telescope, scheduled to launch in the coming years, will have a field of view roughly 100 times larger than Webb's, allowing it to survey vast areas of sky relatively quickly. Roman is designed to study dark energy through observations of distant supernovae and the distribution of galaxies, discover thousands of exoplanets through gravitational microlensing, and observe billions of galaxies to map the cosmic structure. Concepts for even more ambitious future missions are being studied by space agencies around the world. A large ultraviolet, optical, and infrared space telescope, sometimes discussed under names like LUVOIR or the Habitable Worlds Observatory, would be a true successor to both Hubble and Webb. Such a mission might carry a mirror 10 to 15 meters in diameter, substantially larger than Webb's 6.5 meters. A telescope of this scale could directly image Earth-like planets orbiting nearby stars, blocking out the overwhelming glare of the host star to reveal the faint light of the planet itself. It could then analyze that planetary light spectroscopically, searching for signs of oxygen, ozone, methane, water, and other molecules that might indicate biological activity. Whether and when such missions actually fly depends on priorities, funding, technical feasibility, and the scientific results from Webb and other observatories over the coming years. But the astronomical community is thinking seriously about these possibilities, developing the technologies that would be needed, and making the scientific case for why such investments would be worthwhile. The data flowing from Webb and from future facilities will drive discoveries for decades to come. But equally important is the theoretical work needed to interpret these observations and place them in context. When Webb finds galaxies that form faster than models predicted, when it detects molecules in unexpected locations, when it reveals black holes that grew more quickly than theory allows, theorists must develop new models that can explain these findings while remaining consistent with everything else we know about physics. This interplay between observation and theory is the engine that drives scientific progress. Observations challenge existing theories by revealing phenomena the theories did not predict. Theories make new predictions that can be tested by further observations. The cycle continues, each iteration bringing us closer to understanding the true nature of physical reality. What has Webb taught us so far? Perhaps the most important lesson is one of intellectual humility. We thought we understood how galaxies formed, at least in broad outline. We thought we knew the timeline of cosmic evolution from the Big Bang through the formation of the first stars to the assembly of galaxies like our own Milky Way. We thought we had the basic story right, even if many details remain to be filled in. Webb has shown us that our understanding was incomplete in important ways. The universe assembled complex structures faster, more efficiently, and through more dynamic processes than our models predicted. The early cosmos was not a slow, gradual transition from primordial simplicity to present-day complexity. It was a period of intense activity where structures emerged rapidly, black holes grew quickly, and the building blocks of everything we observe today were assembled in remarkably short times. This does not mean that physics is broken or that we need to start over from scratch. Einstein's equations of general relativity still accurately describe gravity. The Big Bang model still explains the broad features of cosmic history. Dark matter and dark energy still appear to dominate the universe's mass-energy budget. The fundamental framework remains sound, but our models of how structures form within that framework need revision. The parameters we assumed, the processes we thought dominated, the timescales we expected, some of these require adjustment, and that adjustment is exactly what good science looks like. Every time observations fail to match predictions, we have an opportunity to learn something genuinely new about how nature operates. The discrepancies Webb has revealed are opportunities, not failures. They are pushing us to think more deeply about how the universe works. They are motivating new theoretical ideas and new observational programs to test those ideas. They are advancing our understanding in ways that confirming our expectations never could. We are living in a remarkable era for astronomy. Never before have humans possessed such powerful tools for observing the universe across the electromagnetic spectrum, from radio waves to gamma rays and everything between. Never before have we known so much about cosmic history. From the first fraction of a second after the Big Bang to the present day and projecting billions of years into the future. And never before has there been so much remaining to discover. So many mysteries waiting to be solved. So many surprises waiting to emerge from the next observation. The James Webb Space Telescope has not broken our understanding of the universe, despite what dramatic headlines might suggest. It has expanded our understanding by revealing that the cosmos is richer, more varied, and more dynamic than we previously appreciated. It has shown us that our models, however successful at explaining observations within certain ranges, have limitations that become apparent when we push to earlier epochs and smaller scales than we could previously access. When you hear that Webb has discovered something impossible, do not think of it as bad news for science. Think of it as the best possible news, evidence that there is more to learn, more to understand, more to discover. The universe is stranger than we knew, and a golden mirror floating in the darkness of space, patiently collecting ancient photons, is helping us figure out exactly how strange it truly is. The cosmos stretches around us in every direction, filled with galaxies beyond counting, stars beyond imagining, planets beyond numbering. Most of this vastness will forever remain beyond our direct reach. The distances are too great, the timescales too long, the energy requirements too enormous for humans to physically explore more than a tiny fraction of what exists. But we can observe. We can collect light that has traveled for billions of years. We can decode the information that light carries about the sources that emitted it. We can build instruments of extraordinary sensitivity and precision, place them in locations of extraordinary darkness and cold, and point them at the unknown to see what comes back. The James Webb Space Telescope represents the current pinnacle of that endeavor. It is not the last word in space astronomy. Future telescopes will be larger, more sensitive, capable of observations that Webb cannot achieve. But for now, Webb stands as humanity's most powerful eye on the distant universe, revealing wonders that no previous generation could have seen, answering questions that no previous generation could have asked, and every answer generates new questions. Every mystery solved reveals deeper mysteries waiting behind it. Every image, every spectrum, every data point adds to the growing mosaic of human knowledge about the cosmos we inhabit. We began this exploration with a simple question about how the James Webb Space Telescope has changed our understanding of the universe. The answer, as we have seen, is profound and multifaceted. Webb has challenged our models of early galaxy formation, complicated our measurements of cosmic expansion, illuminated the processes of stellar birth and death, characterized the atmospheres of alien worlds, and revealed black holes that grew impossibly fast. Each of these discoveries connects to fundamental questions about the nature of reality, the history of the cosmos, and our place within the vast structures of space and time. Each points toward future investigations that will occupy astronomers for years and decades to come. Each reminds us that the universe retains the capacity to surprise us, no matter how much we think we understand. The stars will continue shining. The galaxies will continue their stately rotations. The universe will continue expanding into a future we cannot fully predict. And humanity will continue watching, wondering, questioning, exploring the endless frontier of cosmic knowledge with whatever tools we can devise. The night sky holds more mysteries than any generation will ever exhaust. And that is perhaps the most wonderful thing of all.